So the problem 3 on homework 7 is as follows. The switch in the figure below uh, is closed at t is equals to 0 seconds. Sketch the voltage and current at the right side of the switch for 0 less than t less than 6 L by U. Take Z0 is equals to 50 ohms and L by U is equals to 3 microseconds. Assume a lossless transmission line. Now, so what we know is that this is the switch and it is closed at t is equals to 0. Okay, so what are we supposed to do right now? We have to find the voltage and the current curves for the right side of the switch, which means here in this part. Okay, how do we do that? So the first step is, what does it say about the time taken for the signal to transmit from the load side to the from the source side to the load side? So here it says take Z0 is equals to 50 ohms and L by U is equals to 3 microseconds. Now we know that L is the length of the transmission line and we know that U is the velocity of the wave. Therefore, that means the time taken to traverse the transmission line is 3 microseconds. Let's call it capital T. Okay, so before we go ahead and find the voltage and this current curves, we have to understand one thing. What exactly happens? From the theory that you've read in the class or you've learned in the textbook, if you don't know exactly which part of the textbook to refer to, I guess it's the section 11.7 on the text, page number 592. You will read about how to deal with transients on transmission lines. Okay, that's the page number. Now, so what happens is once you apply a voltage, and even if it's a DC voltage, once you close the signal, all that the voltage sees is the internal resistance of the source and the impedance of the transmission line. The load is not visible to the input DC source. Now, you have to find what is the voltage that appears at this point. Okay, what is the voltage that appears at this point? And then we'll also have to find what happens to the signal once it traverses the entire distance and reaches this point. So you'll see that, okay, we'll find out first what is the voltage at A. So the voltage at A is equals to Vg divided by Zg plus Z0. Now we know that Zg is equals to 3Z0, which is given here, and Z0 is equals to Z0, which is given here. That's the transmission line. We already said that the moment the switch is closed, the source does not see Vg does not see the load. Okay, that is equals to 0.6 Z0 in our present example. Okay, so let's find out what that is. So this is Vg by Zg plus Z0. This gives you the current, multiplied with Z0 gives you the voltage. Okay, so Va is equals to 40 volts divided by 3Z0 plus Z0 into Z0. Okay, so that means it's going to be 40 divided by 4Z0 into Z0. Z0 cancels, 4 tenths of 40, so that's equals to 10 volts. So the voltage at A is equals to 10 volts. Okay, now this is one of the things. Also, we have to understand what happens to this signal as it traverses through the transmission line and reaches the load before we sketch the curve. So once the signal hits the load, it gets reflected back. Now, how does it get reflected back? We can find that out by calculating the reflection coefficient at the load. Okay, so let's find out what is the reflection coefficient at the load. So reflection coefficient at the load is given by ZL minus Z naught divided by ZL plus Z naught. So that is equals to 0.6 Z naught minus Z naught divided by 0.6 Z naught plus Z naught. So this comes out to be about 0.44 Z naught divided by 1.6 Z naught, that is equals to minus 1 by 4. So this is gamma L, that is the reflection coefficient at the load. Now once the signal hits the load, reflects back in accordance with the reflection coefficient, then that signal traverses towards the source, and once it hits the point A, now it gets reflected back from the source side. How do we find out how does it get reflected back by the source side? So we'll find the uh, reflection coefficient at the source side. How's that? How can we find that? That's going to be source side or the generator side is one and the same. So let's call it generator side. So gamma G is equal to Zg minus Z naught divided by Zg plus Z naught. That is equals to so 3Z naught minus Z naught divided by 3Z naught plus Z naught. That is equals to 2Z naught divided by 4Z naught. That is equals to 1 by 2. So let's say a signal of 10 volts travels from here to here. A negative 1/4 of that signal gets reflected back, because that is what the load side reflection coefficient says. And once the negative 1/4 of that signal hits the source side, a positive half of it goes back into the load side. So that is what is happening. So if a 10 volt signal starts here, then let's say 10 by 4 gets reflected back, and 10 by 4 by 2 gets reflected back, like this. So our voltage bounce diagrams give us a detail about exactly what are those numbers. Okay, so now we'll head into the bounce diagrams for this particular voltage. Okay, I'll show you how the voltage works. You can do it for current as it is. Okay, so this is a bounce diagram. You have this as the source side, which is Z is equals to 0. This as the load side, Z is equals to L, capital L, whatever you want it to be. Okay, now along this direction you will see the time. Okay, and we'll mark each of this as we go about. You can start from the top or from the bottom. I guess the professor taught you to start from the bottom, so I'm starting from the bottom here. So at Z is equals to 0, okay, at time is equals to 0, what does the voltage look like? As we said earlier, the moment clock turns 0 and the switch closes, all that we see is a 10 volt signal at A. And we are asked to find out, or we are asked to sketch the voltage and current at the right side of the switch, which means we have to sketch the voltage at A. So at t is equals to 0, the voltage is 10 volts. So let's say that at t is equals to 0, voltage is 10 volts, and that is what propagates all the way to the right side. Okay, now we know that the time taken for the signal to go from 0 to L is about 3 microseconds. Why? Because that is what has been given to us in the beginning. Okay, that's given to us. So what is the signal strength then? That this is called 10 volts. Okay, now this is 10 volts, so it's going in this direction. Now once it hits the load side, it gets reflected back, and it gets reflected back by minus 1 by 4th. So the signal that is going to come back here is going to be then minus 10 by 4. Okay, let's write it on top of the others so that we don't have any confusion. So if this is 10 volts, then this is going to be 10 by 4 volts. Okay, that is about, I guess it's about 2.5 volts. Now once it reaches the source, it's about 6 microseconds. Remember, we have to find out we have to sketch the diagram for 6 times L by U. That is 6 times 3 microseconds. That is about 18 microseconds. So we'll do this. Now once we have the signal at the source, which is about minus 2.5 volts, it'll get reflected back to the load side by how much? Let's say it is going to be reflected by half. So we are going to see a minus 1.25 volt signal here. Okay, and by this time we'll have already finished 9 microseconds. So once we are away from here, uh, once the signal reaches the load, it'll reflect back and we will see a minus 1.25 is 10 by 4, 10 by 4 is 10 by 8, 10 by 8. So basically it's going to be minus 1.25 divided by 4 divided by, okay, it's going to be minus 1.25 into minus 1 by 4, that is going to be 1.25 divided by 4 volts as it goes back. Okay, so now it's already positive now, and once it reaches the source it's about 12 microseconds, and once we go back again, so then it'll be so 1.25 divided by 4 into 2, that is divided by 8 volts by the time it reaches the loading. So by this time it's 15 microseconds. Then again we will go to the source side. Now it is going to be 1.25 divided by 8 into 4. So we'll divide the whole number. Every time it goes to the load, we divide the signal by minus 1 by 4. Every time it goes to the source, we divide the signal by half. Okay, so that means it's going to be minus 1 by 16. Okay, so minus 1.25 volts divided by 16, and by this time it's 18 microseconds. We'll just do another one just to be on the safer side so that we get enough signal. So by this time we will have a signal which is 1.25 divided by so if this was 8, this was 8, my 8 into 4, 32. So okay, sorry, so this was 32 and this is 64. Okay, so this is 64 volts. So all that we have here is the different voltages along the different timelines. Now how do we go ahead and plot the voltage at the required point? So we are required to find the voltage exactly on the right side of the switch, which means we have to plot the voltage at A. So if this is Z is equals to 0 and this is Z is equals to L, we have to find voltage at Z is equals to 0. So let's go ahead and do that. So what happens here? Let's see, we have to find the voltage at Z is equals to 0. Now at Z is equals to 0, the voltage is 10 volts. Okay, let's call this so if this is 2, or I don't know, let's call this 2.5, and this is 5, and this is 7.5, and this is 10. Okay, at Z is equals to 0, it is 10 volts, and up until Z is equal at Z is equals to 0, it's 10 volts, and up until 6 microseconds, it's pretty much 10 volts. So I can write this as almost up until 6 microseconds we have just 10 volts on the source side. Okay, now the moment we cross the 6 microseconds, the moment we hit 6 microseconds and we just go over it, what happens is we have 10 volts initially, and then we have a negative minus 2.5 volts, and then we have a negative minus 1.25 volts. So we add all the three up and then find out what the next voltage is. So that is going to be 10 minus 2.5 minus 1.25. So that is going to be about 10 minus 2.5 is 7.5 minus 1.25 is equals to 6.25. So at 6 microseconds, between 6 microseconds and 12 microseconds, we have the voltage at about 6.25 volts. So let's say this is 5, then we will have 2.5. This is about 6.25 is at the center. Okay, so this is 6.25. So this is where our voltage is going to be. Okay, so between 6 and 12 microseconds, we'll have about 6.25 volts. Now, once we have that, and once we go, it will be the same until 12 microseconds. And the moment we cross 12 microseconds, we are going to have another addition of 6.25 plus 1.25 divided by 4 plus 1.25 divided by 8. We have to add that to the original voltage. Okay, so that is 1.25 divided by 8. So that's going to be 46784. So this is 1.25 divided by 8. This is 1.25 divided by 4 plus. So what happens is 6.25 plus 0.3125 plus 0.46875 is going to give you about 7.03125 volts. Okay, the reason I'm just showing all of this is this is how it is actually done. So if this is 6.5 and this is 7.5, somewhere in between we will have 7 exactly at the center. So that's going to be here, and that's going to prolong up until this point. So what you'll see is, so as we move from 6, 9, 12 to 18, okay, so we will have this until 18, and then the very next moment at 18 we will have how much? So we will have a negative voltage, which is minus 1.25 divided by 32 plus 1 minus 1.25 divided by 64. Okay, so which means 1 divided by, so that's going to be 1.25 into 2 plus 1.25 divided by 64. So plus 7.03125. So this is minus. Okay, so that is going to give you plus 7.03125 is going to be 6.97 voltage. So we had 7 earlier, and then we are going to come slightly lesser than that. Okay, it's difficult to draw anything lesser than that, but let's try this out. Okay, let's say this is 6.97. So what you're actually seeing is the voltage eventually settles down, okay, to something in between. Okay, it was first at 10 volts, and then it came down to about 6 volts, or 6.25 volts, and then it went to about 7 volts, and then again 6.97. So it'll eventually settle down to some value here. Okay, similarly you can draw a line for V at Z is equals to L. We could do it by basically seeing what happens at L. So the first initially until 3 microseconds there is nothing. Okay, you could practically say it is 0, and there is no voltage at the load. So you could just write it as 0. And then what happens at 3 microseconds is that you get a 10 volts and a minus 2.5 volts. That would mean it's about 2.5, 5, 7.5. So between 3 and 9, it is stably at about 7.5 volts, and at 9 it has 7.5 minus 1.25, which is 6.25, and 6.25 plus 1.25 divided by 4, so that is about 6.56. So if this is 6.25, it's going to be somewhere here where it is 6.56. So again, at the load side, you'll see that this is going towards 6.56, and similarly this will again fluctuate a bit higher up and then come lower down, and then eventually it'll also reach a stable voltage. So you see that it takes some time for the transients to settle down, and the whole exercise is to find out like at what time the transients settle down. Okay, so this is how you find the bounce diagram, and this is how you write the voltage curve. You can do the same thing for current. Okay, thank you.